Welcome to AI Paper Slop. Today we are looking at TREX, Tactile-Reactive Dexterous Manipulation, a new paper from researchers at UC Berkeley, NVIDIA, Stanford, and others. The core insight of this paper is that, while current robot foundation models rely on slow, vision-based control loops, true human dexterity depends on ultra-fast tactile feedback. So to solve this, TREX introduces a variable rate mixture of transformer architecture, essentially running a heavy visual stream at 5 Hz to plan, and a fast, asynchronous tactile stream at 20 Hz to react to contact in real time. Backed by a new 100-hour tactile-synchronized dataset, TREX improves real-world contact-rich task success by 30% over existing baselines. Let's unpack exactly how they pulled this off.
Yeah, I mean, it is a massive systems achievement. Like, if you are an ML engineer or, a robotics researcher listening to this, you definitely know the frustration. We've scaled visual data relatively easily, right?
For sure.
We have these massive egocentric data sets. We have powerful vision language action or VLA models that can look at a scene and just know exactly what to do. But reactive, high-frequency, closed-loop control based on touch?
Yeah, that's the hard part.
Exactly. That has remained a massive systems and architecture bottleneck. I mean, vision gives the robot the macro plan, but touch is what actually seals the deal when physics gets messy. Until now, bridging that frequency gap between, what a robot sees and what it feels has been just a complete deployment nightmare.
It really is. Like, imagine trying to thread a needle while looking through a webcam with a 1-second delay.
Oh, that sounds awful.
Right, that frustrating, clumsy feeling. That is exactly how the world's most advanced multi-million-dollar robots experience reality right now. Vision is inherently sluggish when you're dealing with the microphysics of contact. But I actually want to push back on the fundamental premise for a thread.
Okay, go for it.
We are in the era of massive compute. You have companies throwing thousands of H100 at problems. We optimize inference stacks constantly. So if the visual loop is too slow, why can't we just run the visual models faster? Like, why not just brute force a massive VLA to run at 20 Hz or 50 Hz and solve the problem that way?
Well, brute force sounds appealing until you hit the physical constraints of edge compute.
Oh, right.
Yeah, running heavy VLA models at 20 Hz is just computationally prohibitive when you are actually deploying on a robot chassis. Think about what a VLA is doing during a single forward pass.
Doing a lot.
A ton. You're passing high-resolution head view images, wrist view images, proprioceptive data, and language tokens through massive multimodal transformer blocks. And you're doing all of this while constrained by the power envelope and thermal limits of a computer that, well, it has to run off a battery and fit inside a metal arm.
Right, it's not sitting in a server farm somewhere.
Exactly. The latency stacks up rapidly. You simply cannot push that much matrix multiplication through an onboard GPU 20 times a second without the system just, melting down or freezing.
So standard scaling laws just hit a wall when you have to put the model inside a physical body.
They absolutely do. And that's why the TREX solution is compelling, because it acknowledges this constraint rather than fighting it. They use a mixture of transformer or multi-backbone to completely decouple the reasoning.
Okay, so breaking it into pieces.
Right. You have a slow action expert that handles the multimodal latent context. It looks at the cameras, parses the language prompt, figures out the high-level geometry of the room, and ticks at around 5 Hz.
5 times a second, okay.
Yeah. But then you have a fast tactile expert. And the critical design choice here is that this fast expert bypasses the heavy visual network entirely.
Wait, entirely?
Entirely. It doesn't look at the pixels at all. It just feels, and it ticks at 20 Hz, providing that rapid closed loop response.
Okay, so I am stuck on the physical execution of this, though. If you have two different brains, like a slow vision brain and a fast tactile brain, and they're sending commands to the same robot arm at totally different speeds, why doesn't the arm just vibrate and crash?
That's the big question.
Right. Like, how do they asynchronously regress the same velocity target without completely stepping on each other's toes and causing thread collisions on the real hardware?
It's arguably the most mathematically interesting part of the paper. They solved this using a cascaded denoising process within a flow matching framework.
Okay, hold on.
TREX uses flow matching for its policy, but they split the denoising steps between the two networks.
Wait, you totally lost me at flow matching and denoising steps.
Yeah.
Before we talk about the fast stream waking up, give me the ELI5 on what these steps are actually doing to the robot's arm.
Fair enough. Let's break it down. So in modern generative policies, instead of just predicting a single action output right away, we often use diffusion or flow matching models.
Like image generation.
Exactly like that. They start with pure mathematical noise and iteratively refine it, right, denoise it step by step until it becomes a highly precise action trajectory for the robot's motors.
Okay, I'm with you.
In this paper, they use an ordinary differential equation solver with a set number of steps, let's say 10 Euler steps, to go from pure noise at time step 1.0 down to a finalized action at time step 0.
Okay, so if I'm understanding the math here, the slow visual model is doing the heavy lifting of, say, figuring out we need to move toward a cup.
Right.
It processes the camera feeds, runs the giant transformer blocks, and does the first 6 Euler steps. It gets the trajectory like 60% of the way there.
That is a perfect mental model,
Yep.
yes. The slow stream does those first 6 steps, bringing the noise down to a time step of 0.4. It basically gets the macroscopic trajectory into a general ballpark based on vision.
But it doesn't finish the job.
No, it doesn't resolve all the way to a final action. Instead, it stops, and it caches those boundary states as a stationary visual context in memory. The paper refers to this as the KV split.
The KV split.
Yeah. It essentially leaves a note for the fast stream saying, here is the general direction we need to move based on what I see.
And because they're using an action chunk length of 16, meaning the model is predicting the next 16 micromovements all at once, the fast tactile stream can wake up at specific intervals within that chunk to make adjustments.
You nailed it.
The paper mentions it triggers at steps 0, 4, 8, and 12, right?
Right. The fast stream wakes up 4 times for every 1 time the slow stream runs. It grabs that cached state, the KV split, combines it with the real-time tactile tokens coming in from the fingers, and resolves the remaining 4 fast Euler steps to bring the action all the way down to a definitive command at tit equals 0.
Oh, wow. That makes so much sense. The visual tower, like all those heavy transformer blocks, none of that re-executes during the fast tick.
None of it.
The computational cost is dominated exclusively by those 4 lightweight math steps.
Yeah, it is incredibly efficient. But you brought up a crucial point earlier about hardware collisions. On the physical robot, thread safety is notoriously tricky.
I can imagine.
Yeah, if the fast stream tries to read a cache that the slow stream hasn't finished writing yet, you get a memory fault and the robot crashes.
Yeah, so how do they prevent that? Because asynchronous robotics usually results in a jittery, desynchronized mess if the timing is even like a millisecond off.
The deployment runtime detail is vital here. They use a single-threaded request socket and an explicit execution lock.
Okay, an execution lock.
Right. This synchronization mechanism essentially serializes the 2 experts. It guarantees that no high-frequency fast tick will ever initiate until the in-flight slow tick has fully committed its cache and the intermediate boundary state to the shared memory space.
Oh, that's smart.
It is a deterministic way to handle asynchronous execution without locking up the physical hardware. The fast loop might have to wait a tiny fraction of a millisecond for the lock to release, but it ensures the data is always clean and the motors never receive conflicting signals.
So the software architecture works. The asynchronous mixture of transformers solves the compute bottleneck.
Yeah.
But, you can't process touch without physical sensors, and that brings us to the actual hardware representation.
Right, the real world.
Exactly. How is the network ingesting the physical sensation of touch? Like, if you are training an AI, it's easy to conceptualize tokenizing a pixel in an image or tokenizing a word in a sentence. But how do you tokenize the physical feeling of a slipping object?
That is the perennial challenge of tactile sensing. You are dealing with continuous, high-frequency, noisy signals. The hardware they use involves fingertip sensors that output raw, 6-dimensional force vectors.
6-dimensional?
Yeah, that means for every single touch, you are measuring force along the X, Y, and Z axes, plus the rotational torque around those same 3 axes.
Like a lot of data.
It is. So TREX utilizes a Spatio-Temporal tactile encoder to make sense of this. They take these raw 6D vectors, collected over a short temporal window of 16 frames.
So they basically capture a brief movie of the physical forces happening over time. But a transformer model can't easily ingest a massive stream of continuous 6D vectors. It needs discrete tokens, doesn't it?
Which is exactly why they pass this 16-frame sequence through a vector-quantized variational autoencoder, or a VQ-VAE.
Okay, the VQ-VAE.
Yes. It consists of a 1D temporal convolutional network that compresses this continuous force data into a compact, discrete token space. It literally maps the messy physical reality to a specific word in a learned tactile dictionary.
But wait. If they're using a convolutional network to compress the data, they usually share the weights across all the fingers to keep the model small. Right.
They do, yes.
So if the math is exactly the same for the thumb as it is for the pinky, how does the model know which finger is actually feeling the pressure?
That is a great catch. To maintain parameter efficiency, the convolutional weights are indeed shared across all 5 fingers. But to retain the spatial awareness of which finger is feeling what, they inject distinct, learned finger identity embeddings right before the encoding step.
Oh, kind of like positional encoding in language models.
It's very similar to that. The network learns a specific mathematical signature for the thumb, another for the index finger, and so on. So even though the compression math is identical, the resulting token intrinsically carries the identity of the finger that produced it.
Oh, that's elegant. Ultimately giving you one discrete drift-robust token per finger per hand.
Exactly.
But here's my issue with that data. Anyone who has worked with robotic end effectors will recognize this critical problem. Think about how a robot moves. The fingers spend 90% of their time just hovering in empty space.
Yeah, just moving through the air.
Right, moving toward a plate, moving away from a cup. If you train a VQ-VAE on that continuous stream of data, the model is going to realize that the vast majority of the time, the optimal answer is just zero force.
Oh, absolutely.
So how do you prevent the model from getting lazy, learning the non-contact state, and essentially ignoring actual touch? Codebook collapse onto a dominant null state seems inevitable when your data is mostly empty air.
You're describing a classic class imbalance problem just translated into the physical domain. If 90% of your data is empty space, a naive model will just output the empty space token 100% of the time to minimize its error rate.
Right.
The researchers tackled this head-on with a clever modification to their loss function. They implemented a magnitude-weighted mean-squared error loss.
A magnitude-weighted MSE. How does scaling the loss function fix the empty air problem?
Well, standard mean-squared error treats all mistakes equally. If the model guesses a force of 0 when it should be 1, the penalty is the same as guessing 10 when it should be 11.
Okay.
But in tactile robotics, missing a light brush against a feather is not nearly as important as missing a massive shear force when an object is slipping out of your grasp. The magnitude-weighted MSE dynamically scales the optimization penalty based on the actual physical force occurring in the ground truth data.
Oh, I see. So if the robot's finger is just waiting in the air and the model predicts zero force, there's basically no penalty. But if the robot is crushing a paper cup and the model predicts zero force, the mathematical penalty is astronomical.
That's exactly the mechanism.
Yeah.
It assigns exponentially higher penalties to frames that are experiencing high-force contacts. This forces the VQ-VAE's codebook to map diverse, rich tactile sensations.
It has to pay attention.
It really does. It has to learn dedicated tokens for slips, shear forces, and hard stops, rather than taking the easy way out and collapsing onto a dominant null state. It guarantees that when the fingers actually touch something, the tokens produced are dense with meaningful physical information.
All right, so we have a fast and slow asynchronous architecture that bypasses compute limits, and we have a robust magnitude-weighted loss function to tokenize the feeling of force without it defaulting to zero.
Yep.
But an architecture is still only as good as the data you feed it. And this is where the paper just flexes on the rest of the field.
Oh, for sure.
The scale of the T-Rex dataset is staggering. They collected 100 hours of teleoperation data.
Anyone who has had to put on a VR headset and teleoperate a multi-fingered robot hand knows that 100 hours is a massive, exhausting human effort.
I can't even imagine.
It represents over 7,700 trajectories. They broke the human motion down into 22 core motor primitives, so fundamental actions like wrapping, peeling, wiping, folding, and they interacted with over 200 diverse objects.
And what I love about the evaluation tasks is how relatable they are to everyday life. But if you actually stop and think about the physics involved, they are phenomenally difficult for a machine. Take task I, which is flip page.
Oh, yeah, that's a great example.
The text instruction is literally just turn a page of the book from right to left using your right index finger.
It sounds trivial until you try to program it.
Right. To turn a single page of a book, you have to apply just enough downward normal force to gain friction on a single thin sheet of paper. If you press too hard, you grab multiple pages or tear the paper.
Yep.
If you don't press hard enough, your finger just glides over the surface.
Yeah.
And you have to maintain that perfect dynamic force vector while sliding your finger across a curved, changing geometry as the page lifts.
It's wild.
Vision cannot do that alone. A camera cannot see the micro friction between your finger and the paper. It is a purely tactile, deformation-sensitive task.
Which is exactly why the 20 Hz tactile loop is so critical. The vision system guides the finger to the edge of the book at 5 Hz, but the tactile system regulates that sliding friction at 20 Hz. And the grading rubric the researchers use for these tasks is fascinating because it is strictly additive.
What do you mean by additive?
Well, in a lot of robotics papers, success is a binary pass or fail, which can hide a lot of nuance.
Oh, right. The granularity of the evaluation is what makes the 30% improvement so believable. Let's look at Task 4, Apply Toothpaste, just to illustrate how hard they graded themselves.
Oh, the toothpaste one is brutal.
To get full credit, you have to nail a whole sequence of micro skills. The left hand has to pick up the toothbrush, the right hand picks up the toothpaste tube. You have to uncap it, squeeze the paste onto the bristles, and then set the tube down without knocking over the brush.
It is the ultimate bimanual force-reactive coordination task. You have one hand maintaining a rigid, stable grasp on a delicate object, the toothbrush, while the other hand must actively deform a different object, the toothpaste tube, to extrude a substance, all while coordinating the spatial relationship between the two hands based on both sight and touch.
Or look at the wiping task. You get partial credit for just grasping the rag. You get a bit more credit for pressing it down onto the plate. But to get the full score, the robot actually has to wipe the plate until a physical marker is visibly removed.
Very thorough.
It has to feel the surface friction of the plate, maintain constant downward pressure, and coordinate with the slow visual stream to know when the visual target is actually gone.
The results speak for themselves. Across these 12 contact-rich tasks, which span insertion, deformation, force-sensitive interaction, and bimanual coordination, T-Rex achieved an average success rate improvement of 30% over existing dexterous hand foundation models.
30%.
Yeah. In the world of real-world physical evaluations, where chaos and friction ruin everything, a 30% jump is an absolute leap. It establishes a very strong new baseline for what tactile reactive control should actually look like.
So what does this all mean for the future of the field? Obviously, a 30% jump is massive, but one thing I respect about this paper is how remarkably candid they are about what they haven't solved yet.
Definitely. The limitations section is essentially a roadmap for the next 5 years of tactile AI. They are very explicit about the hardware bottlenecks holding the software back.
The physical sensors, right?
Yes, the algorithms might be ready for high-frequency control, but the physical sensors are still lagging. They specifically call out sensor distortion and calibration drift across devices.
Oh man, if you build hardware, calibration drift is just brutal. You can train a model perfectly in the lab, but 2 weeks later, the physical elastomer on the robot's fingertip has degraded or stretched slightly from use.
It happens so fast.
Suddenly, the sensor's resting state isn't reporting 0 anymore. Your whole 0 point is skewed, and the model starts hallucinating forces that aren't there.
Exactly. And beyond sensor degradation, they also note the critical absence of dense palm sensing.
Oh, like the middle of the hand.
Right. Right now, T-Rex relies heavily on fingertip sensors. But think about how a human manipulates a heavy object, like, say, rolling a water bottle across your palm to re-grasp it. That requires high-resolution tactile data across the entire surface area of the hand.
And we just don't have that yet.
That hardware simply doesn't exist reliably at scale yet. Most commercial robotic hands only have sensors at the very tips.
Right. They also mentioned algorithmic limitations regarding the training data itself. 100 hours of teleoperation is a Herculean effort, but teleoperation can only take you so far, right?
Correct. For extremely long horizon tasks, especially those with tight physical tolerances like industrial assembly, pure human teleoperation data just isn't enough. Humans inherently rely on minor subconscious muscle corrections that are incredibly hard to perfectly map to robot kinematics over a network connection.
That makes sense.
The paper suggests that future work will likely need to integrate reinforcement learning, essentially online, trial and error interaction-based refinement, to master those extended hyper-precise contact sequences. Use the teleoperation data to teach the robot the basics, and then use RL to let the robot refine the physics through its own practice.
It is the classic transition from imitation learning to RL to bridge the final gap of mastery. Well, looking at this mixture of transformer architecture and the sheer necessity of 20 Hz tactile loops, it leaves you with a pretty wild thought to ponder. If hardware eventually catches up and we cover humanoid robots in high-resolution, full-body artificial skin that constantly streams tactile data, we need an entirely new paradigm of tactile-first foundational models. Like, will touch become the primary way an AI understands the physical world, or will vision always remain the heavy, slow anchor of AI reasoning? Thanks for tuning in to this deep dive into AI paper slop. See you next time.